All right. Good morning. So this is the lecture for chapter 20. Now, chapter 20 is a little bit different than other chapters we've gone over, right? Chapter 20 is, the way I think of it, is more about an applied chemistry chapter. And so what we're going to do is we're going to focus on taking content that we already know, things like partial pressures, molar masses, densities, things like that. And we're going to try to see them in action. And so we're focusing on the chemistry that's happening in the atmosphere. That's kind of like the context that we're seeing things. But we're really trying to apply things. So we're going to cover most of the theory for the whole chapter inside of this first lecture. And then on Wednesday, we're going to be, or in the next lecture, we're going to be focusing on doing the problem solving, right? And so this is really more like us taking material we already know and then applying it. So we're not really learning any new chemistry concepts, perhaps in terms of calculations, but we will be kind of pulling different things together. And so first, let's define the atmosphere, right? The atmosphere basically consists of four parts. There's the troposphere, right? There's the stratosphere, the mesosphere, and then the thermosphere. And so within each parts of the atmosphere, we get a big variety of chemistry that can occur because they feel different temperatures. And then we also have different pressures as well, right? And so temperature varies a lot, basically where we're living kind of down at the bottom of the troposphere. It's a different temperature, a lot warmer than what we might see higher up, right? Different ones, right? As altitude increases, basically our temperature decreases primarily. And then the pressure also decreases as you go up because the pressure is caused by all of that air lying above us, so that atmosphere. And the higher up we are, then the less we see. Now, the troposphere has a lot of mixing. We get a lot of wind, things like that. The stratosphere, that's kind of like where you would be when you're in an airplane, right? That 30,000 feet or so. The ozone layer is a component of the stratosphere, right? The next ones up are kind of the mesosphere and then the thermosphere. And if you want to think about it, the thermosphere is kind of like the very edge, so it's the farthest away from us. Right? Now, the components of our air, it does vary based on where we are at, right? This is the composition for our dry air near sea level. And you can see kind of like the vast majority of the content is nitrogen, followed by oxygen, and then argon. We do have carbon dioxide and water in there, and that kind of fluctuates based on your location and the time of the day and the year. And so that can change, right? This composition of the atmosphere is also varies based on location, but also vertically as you go up the column. Pretty much heavier gases tend to sink in the atmosphere, and then lighter ones kind of leave near the top, right? So things like helium, we would expect that to vary from argon because they have different densities. And so where we are, the majority of the air is primarily nitrogen and oxygen, and then small amounts of these other ones. And so let's try this out. Would you expect the ratio of atmospheric helium to argon to be larger in the troposphere or the mesosphere? So think about where those are in relation to each other, and then we can move forward from that. And so we should be thinking, well, troposphere is lower than the mesosphere. And so that means that we do see variation. And so we should be thinking, well, helium is less dense than argon, right? And you can think about that in terms of their molar mass. They're both gases, so they both occupy relatively the same volume, but argon has a much higher mass than that of helium for the same amount. And so we would expect that helium is more abundant at the higher elevation, the mesosphere, than that of the argon. So we're looking for C. And so that's our atmosphere. And so within the atmosphere, we're going to talk about 3 cycles in today's class. We're going to look at the nitrogen cycle, the oxygen cycle, and then the carbon cycle. So the first one that we're going to talk about is the nitrogen cycle. And so the nitrogen cycle is a big part because it makes up a significant amount of our atmosphere, but it's very involved in things like plant growth, right? Which is an important part for us because so much of our food comes from plants, right? We start off with plants. You might eat the plant, the animals might eat the plants, we might eat the animals, right? The whole food chain cycle all starts from this part. And so nitrogen goes through a couple of different cycles. It can start in the atmosphere, and then it can get fixed either through a biological process, right, through plants. It can also get fixed through an industrial one, which is the Haber-Bosch process, right? And about 70% of the nitrogen inside your body is fixed through this industrial process, right? We can also get some that's fixed through the rocks, right? And so we'll be looking at these different processes. Basically, as it goes through, it gets used inside of our soil. That soil creates, is used by the plants. Animals eat those plants. We can then return that to the soil when we pass, or we can get denitrified and it can get released. Right? So there's a couple of different ways for it to go through. So these are some simple chemical reactions involved with the nitrogen process, right? So this is what we see through the nitrogen fixing, right? Through atmospheric fixing. This one down here is what we see in the Haber-Bosch process. And so we'll be looking at either of those throughout the process to kind of look at how we might be able to improve on what's going on. And so we can look at whether or not the concentration of our nitrogen, what impact that might have on our kinetics. So if we did it at one temperature or at one area of the atmosphere versus another, we could look at that. We could see if we were to increase our oxygen content, how would that impact our equilibriums? And so there's a couple of different ways that we can kind of look at the nitrogen cycle and focus on that chemistry involved. The other cycle is our oxygen cycle. And the oxygen kind of takes place in a couple of different ways. Oxygen in water on Earth can react in the phototic zone at the top of the water surface to produce CO2, right? So that's kind of what's going on in here. And so basically what's happening is phytoplankton produce those O2, which reacts with the light and photosynthesis, and then we can release that into the air. We, as mammals and animals, we breathe in that oxygen, and we can use that for our energy, right? That's part of our respiration process, so we can take that in. The O2 in the atmosphere also goes into creating things like rust, right? So we get that oxidative weathering down there. And that weathering then gets released as sediments over time. It can also react with our carbon monoxide released from volcanoes to create carbon dioxide. And so what you see both in this cycle and in our nitrogen fixing cycle is that there is this impact that volcanoes have in our atmosphere's chemistry. Right? Volcanoes release a high temperature with a lot of different types of materials that are released from further in the Earth's core. And so there's some unique chemistries that take part in the atmosphere because of the presence of volcanic eruptions. Once we have oxygen, we can also then move up and we can cycle this and turn it into ozone. Ozone is just oxygen, but with 3 oxygen molecules attached. And that plays an important role in preventing ultraviolet radiation from entering the atmosphere. And so our process kind of cycles back and forth depending on what's going on. Now, the reason why we care about our chemistry of our nitrogen and oxygen is that they make up so much of the atmosphere. And they also have very unique chemistries about what's going on with them. And so we're going to be looking at that process. Now, nitrogen is pretty much largely unreactive because it's got this triple bond, this N to N triple bond. And so for us to engage in that chemistry, we have to break that bond, which requires a lot of energy. Oxygen has a lower one and is therefore more reactive. And so that's why we see a lot more oxides than we do see nitrides, right? Now, oxides of non-metal are acidic, like you might have done in the CHEM121 experiment, and the oxides of active metals are basic. Now, things like the aurora borealis, that can be related to this excitation of these nitrogen and oxygen atoms up in the atmosphere. These molecules can get excited, and then when those electrons fall, right, when they return to their unexcited state, then they can release photons of energy in the visible light, which we can see. Now, that absorption of energy is an important process of what makes our atmosphere so important to us. So inside our atmosphere, there's a lot of what we call photochemical reactions. This is the chemical change that occurs when we either absorb a photon or release a photon. Right? And so this can happen when we're doing photodissociation, where we're breaking apart, or when we're doing photoionization, where we're forming ions. Right? But this red line is kind of the solar spectrum outside the atmosphere. It's what we see from the sun, or from our sun. And then this line down here, all of that is what we see down here at sea level. Right? So the top one, that red line, we have to measure this one from space. Once we get a telescope up past our atmosphere, we were able to measure that and record what sun or what light spectra we would have coming in. And this one down here, the second one, the one that's sea level, that's what we see after it goes to the atmosphere. And you can see that there's a big difference there. We see sections where things might be absorbed out, right? Things like this. And that difference is caused from molecules of our atmosphere air absorbing in energy that's being released. And so we have different concentrations because different amounts of that material is getting absorbed. So photodissociation, it's when you absorb a photon, but we're not going to form ions. Instead, we're going to form something called radicals. Right? Now, radicals are a type of atom, right? But basically, they have unpaired electrons. And one of the most important reactions that kind of goes through this process is the photodissociation of oxygen molecules to just oxygen atoms. So you can see here that our atom has a unpaired electron. Right? So we would be 2 unpaired electrons because oxygen would be our 2s. And our 2p, right? So our 2 unpaired electrons. Now radicals can be very reactive because they have those unpaired reactions. Those unpaired electrons, so they can engage inside those reactions. Now this one, this HV, that stands for a photon. And it stands for that because we have to remember that E of a photon is Planck's constant times its velocity. And so when we see that inside of our chemical reactions, they're trying to let us know that we're absorbing that photon. So it's acting like a reactor. On the other side, photoionization, it's a similar process. We're still absorbing a photon, but this time we're going to eject an electron. And so we're going to turn into an ion. Now, if we're losing electrons, then we should know what kind of ion we're going to be making. And so we should be forming cations. And so these are 4 of the big photoionization reactions of the atmosphere. We have nitrogen going to this nitrogen 2+. We have oxygen gas going to O2+. We also have oxygen atoms going to oxygen+. And then we have nitrogen monoxide going to NO+. And you can see that there's different amounts of energy in there. So nitrogen monoxide is our easiest to break. So it's the easiest to ionize compared to that of our oxygen, and then our nitrogen gas is the hardest. And so down here, we can see what kind of wavelength we would have to have in order for that to occur. And so we can have that wavelength or below. Or ionize that particle or molecule. Right? So if we look at it, right, this 80.2 nanometers, if we go back to our solar radiation, that's way down here in our spectrum. So we don't get much of that radiation, but even that small amount can engage in this chemistry and can really impact what we're making. So think about your photoionization. What is going on? Does photoionization lead to the formation of a cation or an anion? Does it lead to a bond breaking? So take a moment to think about that. So photoionization means that we are making ions, and we're doing that by releasing electron. So we're definitely forming cations, right? So that means that we're looking at C or we're looking at D. Now, our electrons, the lower energy or the higher energy electrons are generally our unbounded ones. And so it generally doesn't result in the breaking of a bond. Right? So generally when we photoionize, we will stay together as a molecule. We would just eject one of our unpaired electrons. Sorry, not unpaired, unbonded electrons. So this chemistry involving the absorption of photons, it can be a big part of what's going on inside of an atmosphere, and it can act as a preventative process, which was what we're going to talk about with ozone. But it can be unique for each of those molecules depending on when they absorb. So ozone absorbs radiation between 240 and 310 nanometers. So in this range, you can kind of see the peak over here. The ozone will take in all of that, or will absorb strongly that light that's coming into there, those photons. And it will help prevent those radiation, that UV radiation, from coming to the surface. And so when we have a lot of ozone, it helps prevent things like skin cancer and sunburn because we're preventing that UV radiation from reaching the surface. As that wanes, as we have a depletion of that ozone, then the amount of UV radiation that's coming through increases, and we start to lose that protection. Now, ozone forms from oxygen and that photodissociated O2, that oxygen atom, to come together to form ozone. And this layer occurs in the stratosphere, so much higher up than the troposphere. And so it's right around that altitude of about 25 kilometers. So if we went to go back and look at our part, we're occurring right in here for our ozone. So it's still in a region where we might fly in the plane. Right? And so we see some of that part. Above the ozone, these photodissociation and photoionization reactions that we see them in what we call the solar radiation, right? So in the thermosphere, that very edge of our atmosphere, we see more of these processes. We can see things like our electron that was ejected forming this radical. We can have our photon. Oh, this one's a proton particle. So this is our proton particle. Oh, that's the eraser. That can be released from the sun, and it's coming in, and then it's colliding in, and we're seeing the transfer of energy over, and so then we're getting this high energy state. Yeah. Now, sorry. This isn't a radical. That was the wrong term to use. This is an excited oxygen atom. Right? And so whenever there's that little asterisk, what it means is that we have an oxygen or a nitrogen or whatever it is, right? But it basically means that it's a molecule that's got more energy in it than it should, right? So it means that the molecule is in an excited state. So it's got extra energy in there. So that means that at some point that extra energy is going to come out, right? It could be quite a while. It could be a short amount of time. It depends on how stable it is with that extra amount of energy. And so it could be when that releases that it could release it in several different ways. And one of the ways that it can do that is through that of a photon. Okay? Now that photon we can see. And so in some of the cases, we see that as green and red, right, for oxygen. And that's where we get this aurora borealis. Sometimes it can be that of nitrogen, which is the blue and the yellow, right? And so this is actually the back of a spaceship. This is the space shuttle. And that glow that we see is this nitrogen monoxide releasing photons as it goes from that unexcited state down. So this is all photochemistry. Because we're using photons to drive reactions or is produced by them. We can also see this dissociation, right? The N2 or our N plus and our O2 plus. Right? Now, I'm not expecting you to memorize all of these different reactions, but what I would expect you to do is to be able to calculate things such as your wavelength energies. You'd be able to determine the amount that we would make. But I do expect you to understand the basic principle. The idea that when you're in an excited state, you can release a photon to return to a ground state or an unexcited state. I would expect that you could understand the difference between a photo dissociation versus a photo ionization. Right? And so that's what we're looking for these processes. And so an example of this would be something like this one, which is in your book in chapter 20, right? And so what I would like you to do is calculate the maximum wavelength of a photon that can disassociate an O2 molecule. Now, if you look on your equation sheet, you do have your atomic structure, which has the energy of a photon, so you can use that as well. So the theme is going to be that if we want to figure out the wavelength, then we have to figure out the frequency of that photon. If we want to figure out the frequency, then we have to figure out the energy of that photon. So we know how much it takes to break apart a mole of that bond. And so now we need to change that to just a single one of those bonds. Right? So one bond gets one photon. So when we walk through that calculation, we can take our kilojoules per mole, turn it into joules, divided by Avogadro's number in order to get it into joules per molecule. Then we can plug that in for our energy. We use Planck's constant for our H, and this gives us our frequency. Now with our frequency, we can use the speed of light here. And we can change that into our wavelength. So the idea is any photon with a wavelength of 240 nanometers or shorter will have enough to disassociate an oxygen molecule. But if you're longer, then you won't have the energy required. So just remember that your energy of your photon, it goes up when your wavelength goes down. They're inversely related. This one is having you look at your Lewis structures. So we have O2 versus O3. And so now you want to be looking at your Lewis structures, draw them out, and then try to predict which one will have stronger oxygen-oxygen bonds. So O2 is our first one. O3. Now O3, we should have a total of 24 electrons. Oh, sorry, we should have a total of 18 electrons. That makes more sense. So right now I am missing out on some of those central ones. So I can move this one over. I can form a double bond here. So now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, right? And we do have resonance between this. All right, there we go. So when we're looking at this, remember that bond strength increases with increasing bond order. And so while this oxygen, right, in our ozone has a bond order of 1.5 because we have to add both resonance and we have to divide by 2, the O bond in oxygen has a bond order of 2. So we should expect the strength increases between O2 to O3. So we're expecting a stronger one inside of that O2 because of the higher bond order. Now, you might have heard of something called the ozone hole, right? And the ozone hole can occur over one of our poles. Generally, it happens over our south pole, but it can also happen over our north pole as well, right? And so the ozone hole is because we're seeing some depletion of ozone. And so this was first found in 1974, right? And while this depletion of that ozone, that creation of that hole can result from a variety of chemicals, what we found out in 1974 was that a lot of it happened from these chlorine-containing chemicals. Those chlorine-containing chemicals, they were called CFCs. You might have also known of them as freons, right? But we basically were using them in foams and foam installations, right? They were in air conditioning, commercial refrigerant, solvent cleaning, right? And so right now we try to minimize our release of those because the CFCs get released into the atmosphere and they go up and they start to react with our ozone and they break it down. Right? Now, since 1974, over 100 countries have banned CFCs or restricted their use. Right? But it continues to happen because of the type of chemistry that CFCs engages in. So ozone already is kind of like in this dynamic equilibrium process. We have ozone gas, we have oxygen gas getting dissociated to oxygen atoms. Those oxygen atoms work with our ozone and then a catalyst metal to form, with oxygen gas and the catalyst metal to form ozone. Now, over time, what's supposed to happen is that ozone absorbs in UV light and gets disassociated back into the oxygen atom and the O2, and they can reform. This dynamic equilibrium would keep us at a constant concentration of ozone in the stratosphere. And so we would be taking in UV light to break apart the ozone, and then we could be reforming that ozone. Now, what happened was when we started to use CFCs, CFCs were these chloroforms with our carbons, or with our chlorines, and that chlorine, it starts to absorb in UV light in the same way O2 does. But when it does that, it releases this chlorine atom. It releases 2 of those chlorine atoms. Now those chlorines can then react with our ozone, and it starts to break it down to form this ClO and release this O2 gas. That can then react with our free oxygen to form O2 gas and release that chlorine. And so it really ends up being this ozone and that free oxygen end up making two of these O2s, which backtracks this entire equilibrium because we are going to create a lot of this, but we're removing our concentration of our O, we're also removing our concentration of our O3. So we're basically facilitating this destruction process. The problem with that is that Cl is a catalyst in this type of reaction. So it's not that it does it once and goes away, it can do this over and over and over again. So we've had to really scale back the use of CFCs because while they can be recycled, right, for things like refrigerants, other cases when we're using them for insulation, we can't. You can't recycle them. As soon as you use them, they get degassed, right? They get released either in the aerosol form, or when you're using that foam over time, it will get released into the atmosphere. So there's no recycling part that's possible for it. And so you can kind of see that there's definitely a relationship between them. And that's because our ozone, if you look at where its concentration is for the different sections, ozone's kind of clustered in certain latitudes. When ClO goes up, or ozone concentration goes down. And so ClO is increasing because of that, the CFCs, right? So this is this chlorine from the CFC reacting with the oxygen to form ClO. And we can see that they're directly related to each other, right? If we can prevent ClO production from forming, we keep a lot of ozone. Now, it's not just that it's a catalytic process, it's that the rate, the kinetics of it vastly changes for ozone concentration or for the ozone destruction from CFCs versus that of its normal destructive process, right? So the conversion of ozone to ozone gas is dependent both on ozone concentration and chlorine atom concentration. So the more chlorine atoms we create, the more ozone that gets destroyed because we have more catalyst that's available, right? So while the catalyst is not directly a part of a reaction, it does impact the kinetics of it because having more of the catalyst available does increase the speed that that reaction can occur at. And so since the rate of ozone destruction depends on Cl, can Cl be considered a catalyst for the reaction of equation 18.10? And so if you look at it, equation 18.10 looks like this. And so when we're comparing that, we want to think about, well, can it be considered a reactant or not, right? Now, because we input chlorine and we get it back out, then it can't be considered a reactant, right? Even though it does impact our rate, it's not considered a reactant because it doesn't appear as a reactant or a product. So we can consider it a catalyst. And so we can consider it to be a part of that process, even though if it directly doesn't change. So that's kind of our ozone chemistry. Inside your homework, you kind of will work through some of those processes where you look at what that equilibrium looks like. And so then we can use our KQs, right, or our KPs to look at what those concentrations might impact. We can also look at that impact of a catalyst, right? So the chemistry is pretty straightforward. Now we just want to make sure that we can use some of those values that we've already talked about in chapters 16, 17, and 18 and apply it with this. The next thing that we're going to talk about is the thermal balance that occurs in the atmosphere. Now, the atmosphere, not only does it protect us from harmful radiation, right, as we've seen with ozone protecting us from UV, but it also keeps us warm. Right? So the Earth keeps this thermal balance with its surroundings. So basically, the planet radiates heat out to space, and then we gain heat from the sun, kind of like the inside of a car. Right? The sunlight comes in, passes through our atmosphere. Some of it gets kept inside. All of it gets reflected back out into space. And so there's been a lot of conversation about something called the greenhouse effect. And the greenhouse effect is occurring because when sunlight from the sun is entering into our atmosphere, some of it is getting absorbed by different gases. So carbon dioxide, water vapor are called greenhouse gases because they cause the retention of heat inside of the atmosphere. In the same way that a greenhouse keeps in heat to warm or keep the temperature inside the house hotter than that on the outside, right? And that's why you want to have a greenhouse in colder weather climates, so that way you can keep your plants warmer, so hopefully they can continue to grow at different parts of the year. So you can see here that this big chunk of solar radiation is absorbed by our water. Right? We have some that's absorbed by our CO2. And so anything that's yellow is some part of the solar spectrum that's being absorbed by a gas inside of the atmosphere. And that's going to help us trap it inside of our thermal blanket. Now, the greenhouse effect isn't necessarily bad to begin with, because when we were first starting, we did want some of this heat to be trapped in by the atmosphere. We do want to keep it, as we do want to build that thermal balance. If all of our heat that we gain from the sun was immediately released, then our planet would be very cold as well. So there was a point where this absorption was a helpful thing to us. It created that thermal blanket. Now, not all gases are considered to be greenhouse gases. And this has to deal with whether or not they can absorb that infrared radiation or not. So our two big gases, right, our highest concentrations are nitrogen and oxygen. And nitrogen and oxygen, they can't absorb that radiation. They don't have a spectrum where it's possible for them to absorb it. Water and CO2, on the other hand, even though they were smaller amounts, right? Like our CO2 is down here in this composition by volume. Water really varies based on its latitude or its longitude. They are able to absorb that IR radiation. So water can kind of absorb that in three ways. As that infrared radiation comes in, it can do things which is called the stretch, right? So that's where it can stretch out. It can do things where it can where it can do a wag. It can also do something where it's so we can see this part, right? How it's adjusting. Basically, the oxygen is moving one way, the hydrogen is coming in, and that one's stretching. So an asystematic stretch, we can see them where they're doing it the same, a symmetric stretch. And we can also have what we call the wag, where it goes up and down. Carbon dioxide, on the other hand, it can do the wag, where it's going up and down. It can also do a stretch going side to side. So each of those molecules has a different way that it kind of deals with that infrared radiation. Infrared radiation is more tied in with vibrational impact inside of our molecules. visible light and ultraviolet radiation, that has more to do with your electrons changing your, that is terrible, let me rewrite this. Your visible light and your ultraviolet light, that's more involved with the changing of energy levels by your electrons. And so when we talk about greenhouse gases, we're looking for gases that are able to deal with this infrared radiation. So they have to absorb light inside of that spectrum. It also needs to be at the spectrum of the sunlight that there's spectrum coming in from the sun, right? So if there's no energy being released by the sun, then we're not worried about those molecules absorbing in that band, right? The wider the band or the stronger the absorption rate, then the more of an impact it can have on this greenhouse. And so this can be a good thing, it can also be a bad thing. And so in a lot of places where there's higher humidity, the nighttime temperature remains high. And so why would that be? And so when we look through this, right, water has the ability to absorb a lot of infrared radiation. Now, what that means is that water in the atmosphere absorbs in that IR light and is going to radiate part of it back to the earth as it tries to release it through its wagging or its stretch. Right? Now, when it releases it, then part of it goes back to the earth. So instead of it just releasing it out into the space, we start to create this background or this this reflection of heat back to the surface. And so we're looking at A here. Right? So it's not that the water is absorbing that UV light and radiating it back to the earth. We're not worried about that in terms of temperature. Temperature is looking at our infrared. Now, the reason why this is being talked about now is because of carbon dioxide. And the reason why is because carbon dioxide, we've changed part of that cycle, right? And so that carbon dioxide cycle is part of the carbon cycle, and so we're going to look at that. Now, carbon dioxide, the majority of it is released from electricity production. So it's not you driving your car primarily. A lot of it comes through the electricity production, things like coal power plants, natural gas power plants, right? When we're making electricity. Another 30% comes from us moving around. So that's things like transportation, right? Cars, trucks, boats, things like that. And the other big part is industry. And so industry, some of them just, this isn't about industry creating electricity. This is industry creating other things. So things like cement production or iron production or steel production. A lot of those also involve the production of carbon dioxide. And then the small amount is through things like heating or cooking. So normally in that carbon cycle, what happens is there's carbon dioxide in the atmosphere. It gets absorbed by plants. Those plants can then go through respiration where it might release some of it back out. Or in reality, what's more likely to happen is after the carbon gets fixed by those plants, we see that as it makes wood, right? Things like that. Animals eat those plants. Those animals then release the CO2 as they go through the respiration process, right? We take in oxygen, we combine it with things like sugar, we release this carbon dioxide. And that goes back up into the atmosphere so it can cycle through this process. Now the difference is that before there were these stores of carbon material that would take a long time to get processed before they would be released again, right? Things like oil and natural gas and our different types of shale, right? So as they're down inside that process, what we've started to do is we've been bringing them up, right? We've been pulling out that oil because we've been able to refine it and use it for things like gasoline or plastics. Right? And so now we're releasing even more of that respiration. Instead of that CO2 being sequestered, we're starting to see a change. And so one of the ways that this was kind of first discovered was over in San Diego, and then they've been monitoring it over in Hawaii at the top of a mountain, right? And so you can see that there's kind of this constant cycle that occurs. Right? So within each year, we see a swing between spring to winter, depending on your different processes that are going on. When there's a lot of respiration going on, we can see a natural uptake in CO2. As those things start to decline, then we can see a decrease in that CO2. And so there was a fluctuation. And that fluctuation kind of stumped the science for a little bit because it was hard to see whether or not we had a trend or not, because each year you could see a different high and a different low. And so it was hard to see if it was constantly going up. But now that we've been tracking this for almost 70 years, you can see that there is this big difference over time. That on the average, our average amount of carbon dioxide concentration in the atmosphere has increased. And that creates a larger greenhouse gas impact, right? So we see more greenhouse effect because CO2 does absorb light in the infrared spectrum. And so that infrared radiation, instead of being released in the same amount that it used to be, is being kept more. And so the Earth is gradually increasing. And so over time, the change in global temperatures from 1850 to the present, you can kind of see them here in their 5-year average, is that kind of like green one. And so each year we might see some fluctuation within it, but over time you can kind of see we are definitely trending upwards, right? Especially when you look at from 1960 on, when we started to really monitor that CO2 impact, you can see that change. Now, we think a lot of this could be from CO2, which contributes to about 55% of that warming as modeled. It could also be our CFCs. Even though they're in a small concentration, they absorb so strongly in that infrared radiation range that they can release that. It could be the methane, and it could be that natural nitrogen, dinitrogen oxide, monoxide. What we're not including in it is we're not including things like water, because water really fluctuates. But as water, or as temperature increases, then our water vapor pressure also increases. And so it's kind of creating an impact there as well, right? So when we talk about greenhouse gases, we want to think about which ones absorb in that electricity, or not electricity, that light in that infrared radiation. Okay? So take a moment, think about which ones we've talked about, think about which ones they might be. So remember that greenhouse gases, they're absorbing it because they have this vibrational node. So we can take out things like neon, because we know neon is atomic, right? But what we're looking for when it's asking about our vibrational nodes is that we need to look for something that has a polar molecule. And the reason why we're looking for polar molecule is that for us to have that vibrational motion, we have to be able to create that temporary dipole. Now, if we're completely balanced, it's very hard for us to create a dipole because we don't have we won't be able to create that temporary situation where things are off. right? If we go back and we look at our vibrational nodes, you can kind of see that we're able to create those temporary dipoles kind of by adjusting their orientation, right? So the wag is one way because they become slightly different in their shapes, right? Maybe our stretch is not exactly the same, our motion could be different. Same with our stretch down here, right? Maybe our right doesn't move quite at the same rate as our left. And so we're going to see these temporary dipoles. This wag here, we can also see that change. And so our greenhouse gases have to have that ability to create them. So when we go through and we look at them, carbon monoxide, nitrogen monoxide, and NO2, they're the only polar molecules that we have from that list, right? Neon definitely can't be polar because it's just it by itself. And then chlorine and hydrogen can't be polar because they're the same atom, right? Those other ones, they do have the ability to create this temporary dipole, which is going to allow them to create vibrational motion. So when we look for greenhouse gases, we're looking for things with a temporary dipole moment, or that can create a temporary, we're looking for something with a permanent dipole moment or something that can create a temporary dipole. Now we talked about volcanoes, and that volcanoes are an important part. Now, volcanoes are a big part for releasing sulfides. So they can release sulfate, SO2. They can also release hydrogen sulfide. Right? And so a lot of these sulfur compounds come from our volcanoes. Now, this can be a good thing. Some of them can create a local cooling impact. It can be a bad thing because they might make sulfuric acid as well. Right? So it depends on the situation. Right? But it does introduce new compounds into the atmosphere that might not normally be there any other way. So if we wanted to think about it, what sulfur-containing molecule forms sulfuric acid when it reacts with water, right? So think about what sulfuric acid means, think about what water is, and then we should be able to figure out what needs to happen for that to occur. So sulfuric acid is H2SO4. And so if we're making that from water, then we must also need SO3. And so SO3 can be released by a volcano, can react with the water, and we can use that to form sulfuric acid. So our volcanoes are kind of injecting this into the atmosphere, and that creates different things for us. Now, one way that it might do that is for something that's called acid rain. So acid rain is a chemistry that's occurring inside the atmosphere. Now, it can be caused by our volcanoes, but in truth, most of it is a byproduct of us burning coal or oil. Because we release SO2, and then it reacts in the air to form sulfuric acid. And then that sulfuric acid is normally what makes that acid rain, though some amount can also be caused by nitrogen oxide. So around your average city, you can see that we have some concentration of sulfur dioxide. When we're not engaged in as much coal burning or oil burning, then that decreases and we don't see it as much. And so across the country, oh, jumped around there, sorry. So across the country, we have a different pH from what kind of processes we're engaging in. So you can see that our SO3 from a volcano can react with water to make that H2SO4. Otherwise, SO2 can go through this two-step process. Can really go through a three-step process in order to create that H2SO4. It can first start off reacting with some hydroxide, or not hydroxide, OH, and then that can react with an oxygen gas in order to form the SO3. Right? So it's a three-step process for it to go through. And so when we talk about pH, we're talking about like the pH of your average pH of your rain as it comes down. And you can see over here that the Midwest and has a higher pH compared to that of the eastern side of the country, right? And part of it is that we have this SO2 that gets created, and then the other part is that as we make it, the winds push that SO2 from the western part over towards the east. So it's not that these ones over on the right-hand side burn so much coal and oil more than what we see on the west coast. It's also that the wind helps us travel that to the right. So that acid rain that gets formed isn't necessarily formed over California, because most of our kind of SO2 that we produce is getting pushed inland, right? We're getting air currents that are coming in from the coast. Now, that impact you can kind of see in how things weather, right? And so a lot of things are made out of calcium carbonate or limestone. The more common name that you might have heard is marble, right? Marble is a type of limestone, right? So that very white material, right, that you might see things get made like statues, things like that. Those can be limestone, that calcium carbonate. And so that calcium carbonate is a base. So in the same way that we did that antacid lab, you can see that same thing with the sulfuric acid. Sulfuric acid can then dissolve that calcium carbonate. We release CO2, and the statue itself will corrode. And so you can see kind of this difference of a statue that's been weathered in New York City of George Washington, right? So over those 50 years, you can start to see all of the details getting removed. And so when they talk about clean coal, they're not really talking about carbon dioxide. When they talk about clean coal, a lot of times what they're discussing is this removal of SO2. So what they do is as they burn that coal, they pump in that calcium carbonate to go through that natural reaction to produce this calcium sulfate. And then they release instead just carbon dioxide and water. And so that helps reduce the amount of our acid rain. And so that's one way for us to go through and improve that. Right? And so the need for chemistry evolves, right? When we were first going through burning coal, we needed energy. So they needed to figure out that process. Now we've had to add in these other parts in order to help prevent these unexpected impacts, right? These acid rain type of impacts, our ozone depletion, right? So as you understand those chemistries, then we can help us narrow down our impacts, and we can look for alternative ways to help mitigate those problems. One of the challenges that we had in California was smog. Right? Now, smog is formed by the reaction of automobiles in the presence of sunlight. Right? So normally it happens from two different things. We have nitrogen monoxide and carbon monoxide, and it's reacting with these unburnt hydrocarbons that are being released. Now, that material, that that process can then release things like NO2 or ozone. And both of those are what help create that smog-like look, right? So it reduces our air quality. Now, ozone was something that we wanted to create, but we wanted to create it up in the troposphere, right? Or the stratosphere. We wanted to create it up in the atmosphere where it can protect us when we're not breathing it in. Down at everyday life, ozone can be a lung irritant, right? A toxic chemical. And so we don't want that down in our air quality, right? And so when Los Angeles was struggling with smog, part of it was that we had to reduce our emissions because we were releasing a lot of this nitrogen monoxide, or we were releasing a lot of unburnt hydrocarbons. Let's say that when you used to pump gas, they didn't have that, the vapor catches on them. And then those two things were being able to react with our sunlight to produce our ozone or our oxygen, which was then able to produce our ozone, right? And so when we look at those processes, that photochemical impact, right? Us having that light along with these other primary pollutants, things like nitrogen monoxide or carbon monoxide, allowed for these different smog particles to be produced. You can kind of see that as they started to track this over time, our hydrocarbons, they generally peak in the morning, right? When our rush hour is kind of coming to an end. And then our nitrogen monoxide kind of peaked at 7 a.m., the start of rush hour. Ozone takes a little bit of time for all of those things to occur, right? We have to have that nitrogen monoxide. It has to get released. It then forms with the oxygen gas to make our NO2. That NO2 then has to get broken down by our photons to release that oxygen. And then finally, that oxygen can react with oxygen gas to form those, the ozone. Right? So our concentration, kind of after we did our rush hour, went back down and we would form this one here. We don't see that as often inside of our evening rush hour because there's less sunlight at that moment. And so there wasn't as much to be able to disassociate that process, or to drive that photodisassociation. So looking at our chemical reactions, go back and see if you can identify which one of these counts as a photochemical one involving nitrogen oxides. And it starts that process. So that smog that we're looking at, the first part that we see that actually has a photon is this one right here, step number 3. So the photochemical step is that third one where it's our nitrogen dioxide being broken down into nitrogen monoxide. There we go. And so then the last topic that we're going to talk about is we're going to talk about radon. Right? Now, radon exposure accounts for 54% of natural radiation that people impact. Right? Of radiation that people impact. There's another like 27% that's natural. The other one is medical testing. Right? Now, radon gas basically enters from the natural decomposition of uranium underground, and then it can come up through your basement or your foundation. So radon, how it's produced is through this natural decay. It's through this natural decay of our uranium. And uranium goes through this process. Now, this is our nuclear chemistry that's covered in chapter 19, which we're going to get into next. And so we'll be talking about that as we move forward. Right? And so what happens is that uranium goes through this natural process where it starts to release different particles, and those particles allow it to transition to a more stable state. One of them is as it goes through this thorium to radon, right, process, and then it can reduce that down into polonium. Now, radon, the challenge with it is that it is the short one. It only takes 3.82 days for it to go through that process. So it creates more radiation than a lot of other ones. Even if there's more uranium, the fact that it takes millennia to go through that process changes things for us. Now, the interesting part about it is that we can already start to solve some of these radiation problems without even having to know about that chemical process of nuclear chemistry. We just need to know this one thing. All radioactive decays obey first order kinetics. So we already know the kinetics for a first order reaction. We know that our half-life is equal to the concentration of it. Sorry, I have to find my sheet. And so we know that there's a relationship there between its half-life and its concentration. And so we should be able to calculate our different values just using our kinetics. So we should be able to solve something like this. Starting with 1.0 grams, we should be able to calculate how much will be left after 10 half-lives. Right? And so we should be able to go through and figure out those materials. In this case, we end up with 9.8 times 10 to the minus 4 grams, because each half-life we lost half of the material that was available. And so that's pretty much all of chapter 20, right? Now, I think that the overall content is a little bit on the simpler side. I think the harder part is the application. And so what I've done is I've pulled out some homework questions that I would like you guys to work on, and then we'll talk about them on Wednesday. I've also included in this slide pack some other example questions for you to work on. And you can see here that the atmospheric chemistry is really just one way for us to talk about some of this other chemistry we already know. Right? So what is the concentration of parts per million of water vapor in a sample of air if the partial pressure of water is 0.80 torr and the total pressure is 735 torr? Right? So us talking about the atmosphere and us looking for partial pressure is all tied into atmospheric chemistry, but it's really not that we have to learn something new. This is all material that we already have covered, right? We've already covered partial pressures. We've covered total pressures. So I would definitely recommend that you start on the homework problems, because I think in a lot of ways this ends up being a review, a lot from Chem 120, some of what we talked about for equilibrium. And so this is a way for us to practice some of those things as we get ready for your exam number 2. Okay. Good luck.